Yeah, thanks for the kind introduction. All those, even though Shomik listed out a list of accomplishments, when you work in corporations, none of your accomplishments are really your own. They are all because of the team you work with and the smart people who either collaborate with you or give you their ideas and you implement some of them and work with them. So I have a list of acknowledgements at the end that will show, at least for this purpose, this presentation, all the collaborators we worked with. My talk, I'll just briefly give a history of PHM at Honeywell, the value proposition, the challenges associated with doing PHM. I'm part of the Honeywell Aerospace research group, so a lot of the challenges in aerospace are pretty unique, and I'll list some of those. I'll list out some of the success we had in the past with machine learning and PHM, and then talk about some of the upcoming opportunities, which are the areas we could get expanded as a group and work on new things beyond just equipment health, which is where most of the PHM work had been concentrated. And finally, I'll give a summary of the thing. So Honeywell has a rich CBM history. There are a lot of systems that go on the aircrafts that you fly in that Honeywell has been working on from the aviation perspective, starting from the flight control maintenance diagnostic system, going down to the aircraft information system, the 777 central maintenance system, the 787 crew information system. All these systems basically implement a vehicle level reasoning. Traditionally, these are designed up rather than build using data, but as we go forward, and these systems have been improved with inclusion of machine learning and analytics into them. On the other half, you see the performance monitoring work like we have on the APU, which is available to the airlines in PTMD. The work that Honeywell did with the primes like Boeing on PISMERS, that was a big Army program. And the similar to the central maintenance work, computer work on the commercial ATR market, the CMC that goes on the aircraft, the BizJet aircrafts. In addition, there's a lot of activity we have worked on the HUMS, which is the health and usage monitoring system with mechanical health, which monitors the mechanical health of the rotorcrafts that goes on different platforms such as the Apache, the Chinook, and some of the commercial aircraft. So what is the value proposition for prognostics? If you think so, everybody in literature will say prognostics, and people mean different things when they say prognostics, or at least the capability you end up achieving is of different degrees. Ideally, you would like to detect the onset of the fault, give out a prediction, give out the time horizon about the time to failure, and be accurate about it. That is where when you would be here, but that is generally very, very hard to do for the equipment that's generally fielded. It's not that you cannot detect the fault, the onset of the fault. What is hard is to set the time you have to failure, because the operation and the disturbances or the disturbance factors on the growth of that failure is or fault is not known. So typically, you may be able to detect something there, but definitely by the time you have a consistent signature of the failure, that is when you would want to detect something, and then still have enough warning to impact either your logistics or your maintenance. So to convert, the big value proposition there is to convert the unscheduled maintenance to scheduled maintenance. And that's where having all kinds of maintenance findings helps you, because it helps you close the loop and with the machine learning and discover these signatures that basically can be detected and can provide a trend that give you how well you are doing and when this equipment will fail. So in theory, it's pretty simple. You get the equipment failure results, you have the data coming from the equipment on the aircraft, whether it's engines, APU, avionics, and you collect a bunch of data and then you do your prognostics. In practice, however, that's not so straightforward. The biggest challenge is the data ownership. Different pieces of data are owned and held by different entities. Traditionally, the design data is owned by OEM like Honeywell, who's making the part, Pratt & Whitney, GE, or the aircraft manufacturers like Boeing, Airbus, Bombardier. Then as the aircraft is being flown, you get the data from the aircraft itself at runtime. You also need the on-wing actions, any action which says, okay, I cleaned up this filter, I repaired this, reset this connection. Those are the hardest kind of repair actions that most of the times the airlines don't even bother recording, and that is something that you can see in your data, but it is very hard to say, did they do anything or they didn't do anything. So that data is generally held by the airlines. And then finally, the shop actions, when the part comes for repair, either managed by the airlines or by the OEMs, and the part is finally sent back to the OEM to get overhauled and all. That data is traditionally better collected and more accessible. And all these, and for doing effective PHM, you need the full life cycle data. Otherwise, you will see things in your data, and I'll show some results where you'll say, okay, what happened here? The good news here is that this was the federated scenario before data science became really important and caught a lot of executives' eyes. Now with the new data agreements that go on with new equipment, people are signing off these agreements where either the OEMs receive most of the data or almost all the data that they can think of, and the airlines themselves are very diligent about collecting this data for their own operational improvements. So things are improving, but when you are a traditional company and which has lots of data from its equipment, not all the data that you have can be has all these artifacts. So we still have considerable challenges. Then there is data diversity. So I talked about data coming from the equipment. That's still pretty easy to collect. What else do you really need to do effective PHM? Do you need the weather data? Do you need the data from what kind of pollution was there? Because those things impact the engines. Was there volcanic ash? Some of that data is being currently published by entities like NASA. And the weather data, there are a lot of public databases that the companies can subscribe to or get cleaned up version of those data, but that still needs to be attributed to and accounted for in your prognostics. Then the other key thing, going back to the on-wing action, is how many alarms were there on the typical aircraft? What did the airlines do to dispose of those alarms? And those kind of logs typically were either collected on paper, not collected. That's still a big challenge. and especially when those alarms are generated by central systems, which may not be part of your system. So as things get cascaded through the aircraft, problems with your equipment may show up and another equipment because they were expecting some input or output, and that is very, very challenging. That kind of data is not fully available. Finally, the other challenge, I would say, is with the data labeling and data quality in terms of for us to apply at least any kind of supervised learning methods, we need to have at least a hope of decent data labels. So on the right, these are some of the pictures from our friends at AD, US Army Aviation Directorate, and they show some of the failure modes, mechanical failure modes that come up. And trust me, the one on the bottom is really bad, and those are the cases, but that does not happen most of the times in aerospace. Most of the assets get removed for high time rather than for failure. So if you look at the curve here, which is my which is a typical degradation curve, and before you turn the knee, most of the parts are removed there when they still have remaining useful life as per a layman, but as an aerospace company and aerospace engineers, it doesn't have remaining useful life. So it's pretty hard to detect because you have not yet hit the knee. The trends really may or may not go south. So it's pretty hard to detect those kind of changes. There's also this issue of small sample size. If you think of aircraft, even the most, one of the most successful aircraft like Boeing 737, there are 9,000 plus aircrafts with 737s, and for that many aircraft, how many of those have seen a specific failure mode that you are trying to build your models for? That's still very, very challenging. You'll end up with data sizes that are like, you have 20 cases, and that is a very good day scenario, and sometimes you have 4 cases. And so that is a very, very, that's still pretty challenging, especially if you are trying to do any kind of supervised methods. Then for the mechanical equipment, most of the times there is no teardown analysis. Most of the equipment do not have teardown analysis. Reliability findings don't get fed back. So finally, when the equipment comes to the shop, depending upon for the engines, somebody does inspect them and say, hey, what is working, what is bad, how good or how bad it is. But when you go back to the small valves, small solenoids, it just gets chucked off because it's a low-cost part. Doing a teardown analysis is not possible. But that is the kind of data that will help all of us improve some algorithms, but that is not available. Going to the avionics part, still, mechanical story is still better than the avionics. The electronics and the electrical systems is still a harder problem on the aircraft PHM because in terms of prognostics, since things cascade more easily in avionics or electronics, it's hard for us to have all the data set that is required. Again, think of the aircraft as a federated system. Honeywell makes a box, GE makes another box, and the aircraft avionics backplane may be made by Thales or some third company, and that's where the big challenge is. You don't get all the avionics data back to you. Finally, all that, whether it's electrical or mechanical system, they are all impacted by environmental conditions. What the aircraft is doing, what kind of controls it has, whether the cooling systems are working, what kind of pollution you are operating in, and all those is traditionally has not been collected at all. So given those limitations, we still have had some success, and where I would say the most success has been with the industry is in the terms of the performance monitoring applications which are used for predicting the eventual failure or degradation of the engines and APUs, which is just another engine on the aircraft. So, and again, Pratt and GE and Rolls also have had success in this area. So, if you look at this chart, what we are showing here is that with analytics here, there was a 17-point increase in our ability to predict severe wear, where the wear actually contributes to the, so if you have a normal wear, the part can be rebuilt, whereas with the severe wear, you may have to scrap the whole part, and you cannot rebuild the turbine back up, and that's basically replacing the turbine, so it costs a lot. So where this helps us is with the APU companies like Honeywell with performance trend monitoring can save a lot of money. I'll talk next about a few of the research programs that we had worked on in the past and which had interesting data mining questions that we are trying to address. So the first one is the vehicle level reasoner program. So we developed a vehicle integrated prognostic reasoner. If you think about all those platforms that I showed with the CMC, the central maintenance computer, the central maintenance computer works as a detection system for diagnostics. So when certain any avionics box that is connected to the, or what are called member systems connected to the central maintenance computers put out a fault message, the central maintenance computer essentially looks at the fault message and disambiguates and says, this is the root cause. So when multiple systems are reporting a fault, that's where the central maintenance computer says, hey, this is a fault with this system. I've reasoned out because this is how the system is architected. What we did on the NASA program is, what NASA challenged us to do is, okay, going forward, how would you incorporate prognostic information if it were available on the aircraft? How would you reason with that? So that was the main focus of the vehicle integrated prognostic reasoner. As a part of that program, we were also addressing the challenge that NASA had is in automated discovery of precursors for safety issues. A lot of data that we had collected, and the data that we were using there, this is a data set that we made available to NASA. Anybody can go to NASA's Dashlink website and download it. It's pretty hard to get anything from Dashlink, but it's still there. So this is 35 tail regional aircrafts with 188 parameters collected from the aircraft, different rates for depending upon what are the inputs. The engine, it has all the engine data. It has a location of the aircraft. It has many discretes along with it, so you can see how the aircraft is being flown. And we had some 5 years worth of data that we used for the Viper program, and we used on a couple of other programs now that we had this data with us. The other data set, I will talk a little on the other programs further, is the HUMS data. So HUMS data is a vibration data that comes from the mechanical systems. So it's a high frequency data set, typically collected tens of kilohertz. And it will be monitoring the engines, the gearboxes on the rotorcraft, and find out detect different failure modes on that. So the going further with the wiper approach, what we are showing here is a system reference model. So CMC basically is a lookup. If you think of symptoms to failure modes to corrective actions, so it's kind of a lookup table that the reasoner has, and this model in the most glorified form could be a full Bayesian model, and in some simpler forms, what we used on Viper was a naive Bayesian model for the faults to evidence to corrective actions kind of a lookup. And what we were trying to do with the data mining piece is using the off-board data that we showed, improve this model further. So this is the work that was done by Vanderbilt University. Professor Gautam Biswas and his team at Vanderbilt worked with us on this. And we related the SIS data, which is basically a safety data set that is voluntarily reported to FAA. It has all kinds of serious problems that the airlines report to the FAA. We related that and the shop findings, limited shop findings that we had for this data set to find out some critical problem. One of the critical problems we were looking at was the in-flight engine shutdown that happened on one of the aircraft. What is pretty funny about, or good about this case, is that there is an in-flight engine shutdown. This aircraft had 4 engines, and if you looked at the aircraft acceleration profile or the flight profile, nothing really shows up on those, except that there's an engine failure and the engine is shut down. So with our data mining approach, basically using the tree-augmented naive Bayesian network learning, we could detect this failure mode some 40 flights prior to the event. And so we could confidently say that some 30 to 40 flights prior to the in-flight engine shutdown, we can find this event and basically detect it and raise an alert that will help turn this, avoid this opportunity event. There were some other cases that we looked at, and what I'm showing is the kind of evidences that we are finding, and when trended over time, you could see the light off, the engine light off problem keep on coming up. In the first one, there was a peak EGT exceedance problem that would come, and then the idle speed would be higher, and all that together showed that there was a over temp problem that was going to happen eventually that would cause the engine to shut down. The same thing with the blade brake and the fuel manifold rupture problem. But again, these were just 3 cases, and for each one of them in our data set, I think for the fuel metering we had probably total of 4 or 5 cases where one had the in-flight engine shutdown, others didn't have. And that is the point. For all of these, it's very hard to go back and say, is there a statistically significant sample set that you have? All the results that we are showing is with cross-validation of the data set, multiple cross-fold validation of the data set. It's not absolutely blind validation. You cannot do that. The other work that we are doing, we did recently with the US Army Aviation Engineering Directorate. So Honeywell is the supplier of HUMS, health and usage monitoring systems on the Apache. As such, when AD was trying to get more mileage out of the HUMS system that they have on the Apache, the Blackhawk, the Chinooks, they were trying to say, how can they improve the performance of the humps? Currently, the way the hump system works, it looks at it looks at the vibration signal at high frequency, it calculates some condition indicators, and those condition indicators are then have fixed alarms for a given platform, and that's how you detect a failure. What AEDs said was looking at, can they use machine learning and these advanced models that everybody is talking about and can they really improve the performance of the hump system? Can we detect failures better? Can we have lower false alarm rates than humps? And as a part of this approach, AED worked with all the hump suppliers on different platforms, and they themselves built many models. They presented some of the results in 2016 workshop, so that paper is also referenced, and you guys can go and take a look at that. I'll talk about the model that was that we had developed for them. And so they had an interesting way of plotting their final results, which I personally liked a lot. So what this shows on the left are all the points at which you got data from different tail numbers. So each row here shows a gearbox that may be on a different helicopter. And each data point from as you move along the row is a download from that helicopter at that time. So you can see for a long time some of those platforms don't download data because they just forgot or whatever, or they may not be flying. So we don't know, we don't have any way to look at that. So time goes left to right. The AED guys are also the ones who determine the airworthiness of these platforms. So when they determine the airworthiness, those are how they generated the truth at removal label that is in the middle column. And basically the prediction ratio shows how many times you predicted healthy versus unhealthy. So this is a pretty interesting chart, but in a sense, the message I want to drive here is that they tested more than, I would say, 30 different types of model using some convolution networks, all kinds of boosted trees, gradient methods, all kinds of classification methods. And this method that was doing well was the XGBoost method. And I think part of the problem is not because the other methods are inferior, because the data you have is very limited. So what you can do with that is also pretty limited and challenging. The other aspect of it is going back to that bathtub curve that I was showing about assets getting removed before hitting that knee. That means your signal to noise ratio is really high. You have a lot of noise in your data, so it's very hard to segregate the faulty and the healthy cases. But anyway, they have fielded that, and their plan of action is to keep on observing how these systems do on live data coming in, which is, I think, the great thing to do for all these systems. Again, some of the other things that I wanted to show here was work we had done with the same data set that we talked about from the regional airlines. And here we are looking at in more in depth at what we had already explored in Viper, namely the fuel control unit failures. And this we were doing as a part of a FAA contract, where FAA had challenged us to basically talk to them about how industry thinks about prognostics and how we think we will be using prognostics. So These charts here on the left, it's the engine speed at startup. So the way, again, you can go back and look in the literature. The fuel controller unit problems are most easily detectable at the engine startup, and that's where we are looking at the startup profile of the engine and both the speed and the exhaust gas temperature, and making some determinations and computing some condition indicators based on that. What I'm showing here is the post replacement, then 30 runs before the replacement, and 200 runs, up to 200 runs before the replacement from. So the idea here is that when you look at this, for this kind of problem on this engine, you can see that there was some indicators that were showing up before, so the profile before replacement and post replacement look very different. However, in terms of if you had to draw up a good prognostic indicator, there's not too much difference between 30 runs before the replacement and 30 starts before the replacement and 200 starts before the replacement. There are some significant differences, but that's what we'll try to explore and show some more results on. For the good case, you can clearly see that at time 0 where the replacement happens, your trends change, and the population is doing pretty good after that. So basically, at the high level, what it means is that once the engine has a fuel controller problem, basically there are two types of problem that can happen. The controller can be either sluggish or fast. In this case, the controller is not able to control the process, so it's very fast, and you hit the peak temperature very fast, and the controller keeps on doing this compensation till you actually, the fault progresses to a point where you actually saturate the controller, and that's where you get an overtemp and the engine will shut down. So again, the point I'm trying to show here is you look at this data and you'll say, okay, the fast start is can be segregated from rest of the data. That's good. Can we really segregate the overtemp? Maybe, but the slow start, just looking at these two parameters, the slow start may be a little harder. But at least for this case, I would say it was working pretty good. Then you go and apply this to a whole bunch of other engines, and then you find plots like these. What the plots here are showing is that in the data you can see there is a clear jump at, and we are looking at 4,000 flights. So first thing you'll observe, there is a seasonal variation you can see on the top. As the seasons change, things vary, that you have to account for. The other thing you will see that in the data, there are these jumps that happen that happen every now and then, but we had for this data that we collected from 2002 to 2007, we had no shop records that aligned with it, and that was the problem of using historical data. Because going forward, it is easier to say, oh, maybe we would not have had these problems, but at that point, it was very challenging. Some of the work from the non-aerospace examples I'll talk about is a single turbine. This is the wind turbine anomaly detection program. Again, we had put a hum system on the wind turbine and gathered a lot of data from wind turbine, wind farm, and we were looking at, for the Department of Energy, and we were looking at can we find out, do enough prognostics and find out failures on the wind turbine. Again, you see the type of models that were developed here were mostly PCA, self-organizing maps kind of models. For the single wind turbine, the results look pretty good. When you go to, in addition, we also developed the power curve analytics, and where the power curve analytics was interesting is that the simple analytics could help you detect failures 20 days in advance to the semi-annual maintenance. So here again with the other models, along with those, there's a lot of statistical based models that were used here. Now you take one wind turbine analytics and try to apply it to a wind farm. What is the bigger challenge here? So the big challenge here is that not all the turbines operate similarly. They may be, some turbines may be downwind from others. So they may share same operating conditions, because operating conditions is not exactly the same as you go over the landscape. And that's where the key is to find out the turbines that had a similar form of similar operation, and so that you could group those together and come up with a performance model for them, rather than come up with a generic performance model that is applicable to all turbines. And this basically shows how some of those groups were selected. And what we found is that when you look at the geographic models that were coming from slightly more geographically distributed setup, but still along the same similar topology, those models were doing much better than other models. So that was the key to getting a better wind turbine PHM model working. And these are some of the results. I would not go into that, but this shows which ones were working better. We had a bigger presentation on this on one of the PHM conferences, and that could be found online too. It's on my reference list. Again, going back to the non-aerospace example, a lot of the work on the industrial side that some of the colleagues I work with have done started with this big program called the abnormal situation monitoring. And this one was basically looking at industrial accidents or fires, such as fires, explosions, and how do you help refineries and oil platforms to detect this abnormal situation and mitigate them, so that you don't have these incidents at all. So so this is one of the interesting findings they had, is that 80% of the accidents are in part attributed to actions of people because they are caused by omission so the human is the cause of the problem. But the paradox really is that better automation is needed for the processes, so that you don't have humans involved so much. But the more you automate your process, when things go bad, humans have more difficulty understanding what has gone bad, and that leads to more errors. So that is the reason for me to include these slides was really to bring out this paradox as we look forward, is to not only have machine learning that works, but also have systems that are basically understandable from the human perspective. So to have it more explainable. If you think about, okay, we have had success and we still apply PHM to all our equipment, but where else can we? Where else is some of the opportunities in aerospace where they are beyond the equipment health? I think one of the big areas where health monitoring or has not been directly applied is for operational safety kind of thing. And again, we do it, but those are generally in support of operational safety rather than directly for operational safety. Here's a classic example. If you look at this, this slide here, on the right, you see the 3 degrees visual slope approach. And this is the data coming from the enhanced ground proximity system, warning system, which is basically a system on the aircraft that helps the aircraft not fly into terrain. So when you think about aircraft coming into land, there is a system on the aircraft that tells the aircraft it's going to land short, or it is going to hit a mountain, or things like that. Before the introduction of this box, there were considerable loss of aircraft, and that has really come down a lot over the last 20 years after the introduction of this technology. But what still is never reported is all these flights that that this box went off. You know, the warning went in the cockpit. This was never recorded. Some of this data was available, and the data set I'm showing is the data that OEMs like Honeywell could download from their own boxes, but it was not shared. I think with more connectivity that is coming to a lot of domains, this kind of data is now more available, and that will enable a lot of the PHM for operational safety aspects. Some of that, and NASA has done actually a lot of work on this themselves and with their collaborating partner. They have looked under the Aviation Safety program at things that you will call abnormal takeoff, abnormal landing, go-arounds, things like that. And the key there is to find out, apply the same kind of techniques that we use for equipment health, and find out conditions that cause either a high energy takeoff, a low energy takeoff, or high energy landing, all those kind of things that eventually are unsafe. And in most of those cases, what ends up happening is that today that the aircrafts do land fine because the pilot does take eventually evasive action or corrective action, but they are still a concern, especially when you start thinking about more traffic in the national airspace. With that in mind, there is other set of programs where as you look forward, there's more challenges, and NASA is again on the forefront here. And there are 2 programs I just want to point out. They're doing this work with ACAS, which is which is a standard that looks at both for the UAVs, which looks at both the cooperative and uncooperative traffic, and basically does a sense and avoid. That is pretty challenging. That has a lot of analytics associated with it. I think currently, if you look at what MIT and other universities and what NASA has been publishing, most of them use explicit aircraft dynamics kind of model, which are either identified or just identified, but there is a lot of analytics and a lot of anomaly detection opportunities in that workspace. We have a program with NASA where, and NASA has a very big program on the airspace anomaly detection as the airspace gets to the next gen, where the traffic is expected to grow multifold. You would not have an air traffic controller looking at all the aircraft and telling them where to go. You need automated systems to do that and point out where is the anomaly in the system. I think there is a big opportunity in that space, at least as far as the technical work is concerned. So that brings me up to the final slide in my presentation, where in summary, I would say that machine learning has been used in PHM for a very, very long time. All kinds of analytics has been done for PHM. The big challenge there is that traditionally we did not get a lot of the data that is required to do PHM very effectively because they were held by multiple stakeholders, the airlines, the service shop, the OEMs, and none of which shared the data, and some of them didn't even collect the data. So that has changed somewhat, or definitely changing. The other challenge used to be that putting sensors on the aircraft was like, okay, everything was a weight discussion. You couldn't put sensors. It was a reliability question. And for the first time, I would say that at least in terms of the talk, people are saying, okay, we'll consider a new sensor if it will help us get some health management objective. So things are definitely moving in a very positive direction there. Still, that would not save us from the challenge of having sparse data. There are only n number of platforms that are flying. If you think about 777, there's like 1,500. Some of the newer aircraft, maybe 5. So how do you overcome that challenge? You definitely need better approaches that can deal with this imbalanced data sets, sparse data set. Anomaly detection is a good way to go for a lot of the things, but it's hard to justify the end. So it's still pretty challenging because in the end, people want directed recommendations, something that somebody can go and fix, and anomaly detection may not help you there. The machine learning approaches that we need in aerospace, at least, need to be very, very explainable. Otherwise, we'll be troubleshooting the PHM results themselves. I will say there are new opportunities in thinking of PHM beyond the vehicles, the engines themselves, thinking of the operations, the whole aircraft operation, thinking of the airspace, again, the supply chain, everything that has operational data. That is where I think there is a lot more opportunity. The data may be difficult to come by, but there is a lot of data that is being collected there. And since you would be looking at the operational failures rather than the equipment failures, again, you will not have the sparse data challenges. Finally, with autonomy and adaptive systems that is being considered, especially if you think about UASs operating in the national airspace, there will be a push to more autonomy and more adaptive systems, whether we like it or not. I think machine learning there has a big role that can help build confidence in these systems. And for that, we need to know if the machine learning itself, the systems themselves are provable, bounded, and all those nice properties. And that is, I think, a continued research challenge. And okay, these are all the people and programs that I referred to. So it will be there in the presentation. Thanks.
Thank you.